Hey folks, today we'll be covering categorical response variables with more than two categories, starting with the case where those categories have no natural ordering. So far, our binary models, the Logit and the Probit, only handle a response with two outcomes, but plenty of responses have three or more categories, the mode of transport somebody chooses, or a medical diagnosis. These are nominal responses. Car, bus, and bike are simply different labels. None of them is higher or lower than the others, so there's no ordering for a model to lean on. We'll start by representing nominal categories with dummy variables, then build up the generalized Logit model. From there, we'll look at the multinomial Logit model and finish with two variants that relax its assumptions, the nested Logit model and the mixed Logit model. Let's dive in. A nominal dependent variable is a categorical response that falls into one of several distinct categories, where those categories have no intrinsic ordering. A classic example is the choice of transportation mode, car, bus, or bike. None of these is higher or lower than the others. They're just different. Another example is the outcome of a medical diagnosis, disease A, disease B, or disease C. Again, there's no natural order to these labels. That lack of ordering is the defining feature. To model this kind of data, we use multinomial models, which extend binary logistic regression to handle multiple categories. One quick terminology note. Data with more than two categories go by several names: multi-category, polycotomous, or polytomous. They all mean the same thing, and any of them can show up on the exam. Before we get to the models themselves, let's recall how we encode a qualitative variable with more than two levels. Recall that when a qualitative predictor is binary, a single dummy variable is enough. When it has more than two levels, one dummy variable can no longer represent every possible value, so we create multiple dummy variables. Suppose we have a variable representing region with levels east, south, and west, and we're predicting credit card balance Y. With three levels, we create two dummy variables, and we leave one level out as the baseline. Here, we'll leave out east. The first dummy variable, xi1, equals 1 if the ith person is from the south and 0 otherwise. The second dummy variable, xi2, equals 1 if the ith person is from the west and 0 otherwise. Notice that someone from the east has both dummies equal to 0. The regression model is then yi equals beta 0 plus beta 1 times xi1 plus beta 2 times xi2 plus the error term. Writing that out level by level. For someone from the south, the mean is beta 0 plus beta 1. For someone from the west, it's beta 0 plus beta 2. And for someone from the east, both dummies are 0, so the mean is just beta 0. So beta 0 represents the average credit card balance for individuals from the east, our baseline. Beta 1 represents the difference in average balance between people from the south and those from the east. And beta 2 represents the difference in average balance between people from the west and those from the east. Every coefficient is a comparison against the baseline level. The generalized Logit model is an extension of the binary Logit model that handles nominal variables. It models the log odds of one outcome relative to a reference category. For j equals 1 through c categories, the generalized Logit model defines a linear component Vij equal to the vector of predictors xi transposed times the coefficient vector beta j. Let's break that down. Vij is the linear combination for category j and observation I. Xi transposed is the vector of predictors for the ith observation. Beta j is the vector of coefficients for category j, and c is the number of nominal categories in the response. The key thing to notice here is that each category gets its own coefficient vector. That will matter when we compare this to the multinomial Logit model shortly. Now, Vij is just a number. To connect it to the nominal response, we convert those numbers into probabilities. The probability that observation I belongs to category j is the exponential of Vij divided by the sum of the exponentials across all c categories. Exponentiating guarantees every term is positive, and dividing by the total forces the probabilities to sum to 1 across all C categories. That's exactly what we need for a valid probability distribution over the categories. There's one more piece we need before the model is fully specified, a constraint that pins down the coefficients. Recall the linear component we just built. Every category J gets its own coefficient vector beta j. The constraint we're about to add applies to the very last one of those vectors. To make the model identifiable, we assume that the coefficient vector for the last category, beta c, is exactly 0. That immediately implies the exponential of VIC is the exponential of 0, which is 1. So the probability of landing in category C is simply 1 over the sum of the exponentiated linear components. Category C is known as the baseline or reference category. It's worth checking a special case. Suppose there are only 2 categories, so C equals 2. Then the probability of category 1 is the exponential of VI1 divided by the exponential of VI1 plus the exponential of VI2. Category 2 is now the baseline, so beta 2 is 0, which means the exponential of VI2 is just 1. Substituting that into the denominator leaves the exponential of VI1 over 1 plus the exponential of VI1. Write Z for that single remaining linear predictor, xi transposed times beta 1. The probability becomes e to the z over 1 plus e to the z, which is the same as 1 over 1 plus e to the negative z. And that is exactly the logistic function we met in the Logit and Probit models video. With 2 categories, the generalized Logit model collapses right back down to the ordinary binary Logit model. So the generalized Logit is a genuine extension of what we already know, not a different model. Now let's interpret beta j. Take the log of the ratio of the probability of category J to the probability of the baseline category C. Because the denominators of both probabilities are identical, they cancel, and we're left with Vij minus Vic. And since beta c is 0, Vic is 0, so the whole thing reduces to xi transposed times beta j, exactly the linear component we started with. So each beta j captures the change in the log odds of being in category J compared to the baseline category C for a 1-unit change in the corresponding predictor. Fries describes this as the proportional change in the odds ratio, and you may see it worded that way on the exam. The generalized Logit model is actually a special case of a broader model, the multinomial Logit model, also known as the conditional Logit model. Consider a choice scenario where an individual I faces C alternatives. We let xij be a vector of explanatory variables specific to the jth alternative, and beta be a vector of parameters that does not depend on j. Look carefully at where the j subscript sits. Here, it's on the predictors, not on the coefficients. The explanatory variables change from alternative to alternative, but a single beta applies across all of them. Let's put the 2 models side by side, because this distinction is the whole point. The multinomial Logit model assumes the same set of coefficients for the explanatory variables across all alternatives. The generalized Logit model allows a different set of coefficients for each alternative, which gives it more flexibility to capture variation specific to each choice. One practical note: a statistical package that performs multinomial Logit estimation can also perform generalized Logit estimation, since the generalized Logit is just a special case. Let's work through an example that makes the difference between these 2 models concrete. An individual is choosing between 3 modes of transportation: car, bus, and bike. The choice depends on 2 explanatory variables: travel time in minutes and cost in dollars. Here's the data for this individual. The car takes 30 minutes and costs $5. The bus takes 45 minutes and costs $2. The bike takes 60 minutes and is free. Let's start with the multinomial Logit model. In the multinomial Logit model, the coefficients for travel time and cost are assumed to be the same across all alternatives. Suppose the estimated coefficients are beta 1 equals negative 0.05 for travel time, and beta 2 equals negative 0.2 for cost. Both are negative, which makes sense. More time and more cost make an option less attractive. The linear component for each mode is beta 1 times the travel time plus beta 2 times the cost. Let's compute all three. For the car, negative 0.05 times 30 gives negative 1.5. Negative 0.2 times 5 gives negative 1. Adding those, vcar equals negative 2.5. For the bus, negative 0.05 times 45 is negative 2.25. Negative 0.2 times 2 is negative 0.4. So vbus equals negative 2.65. And for the bike, negative 0.05 times 60 is negative 3. The cost is 0, so the second term drops out entirely. vbike equals negative 3. Now we convert these into probabilities. Each probability is the exponential of that mode's linear component divided by the sum of the exponentials across all three modes. Running the numbers, the probability of choosing the car is about 0.405, the bus about 0.349, and the bike about 0.246. Notice that these three probabilities are fairly close together. Hold on to that because it's going to change when we switch models. Now let's run the same data through the generalized Logit model, where the coefficients are allowed to differ for each alternative. Here, the coefficients for travel time and cost can differ for each alternative. For the car, the time coefficient is negative 0.04, and the cost coefficient is negative 0.15. For the bus, negative 0.06 and negative 0.25. And for the bike, negative 0.07 for time and 0 for cost, since the bike is free anyway. For the car, negative 0.04 times 30 is negative 1.2, and negative 0.15 times 5 is negative 0.75. So vcar is negative 1.95. For the bus, negative 0.06 times 45 is negative 2.7, and negative 0.25 times 2 is negative 0.5. vbus is negative 3.2. And for the bike, negative 0.07 times 60 is negative 4.2. vbike is negative 4.2. Applying the same probability formula, the car comes out at about 0.718, the bus at 0.206, and the bike at 0.076. Putting the two sets of probabilities side by side makes the difference obvious. In the multinomial Logit model, the same coefficients apply to every mode, which produces relatively balanced choice probabilities. In the generalized Logit model, the coefficients differ across alternatives, which leads to much more pronounced differences and better captures variation in preferences for each mode. Let's look at how to interpret the parameters of the multinomial Logit model. To interpret the parameters, we compare two alternatives, h and k. Taking the log of the ratio of their probabilities, the common denominator cancels again, and we're left with the difference in their predictor vectors times the single coefficient vector beta. So beta j can be interpreted as the proportional change in the odds ratio, where the change is the value of the jth explanatory variable moving from the kth alternative to the 8th alternative. This leads to a notable feature of the multinomial Logit model called independence of the relevant alternatives. Because the ratio of any two probabilities only involves those two alternatives, it does not depend on the presence or characteristics of any other alternative. Here's what that means in practice. Suppose an individual is choosing between taking a bus or a car, and we care about the ratio of those two probabilities. Now we introduce a brand new transportation mode, a train. Under the multinomial Logit model, the relative odds of choosing the bus versus the car do not change at all. The train is treated as completely irrelevant to that comparison. This property can be restrictive and unrealistic in many real-world situations, because it assumes all alternatives are perceived as completely independent from one another. In reality, a train is a much closer substitute for a bus than it is for a car, so adding it should pull more share away from the bus. The nested Logit model, which we'll cover next, is designed to fix exactly this. The nested Logit model addresses the problem of independence of irrelevant alternatives by grouping the alternatives into nests, which reflects a multi-stage decision-making process. Continuing our transportation example, the nested Logit model might group the alternatives into two nests: private transport, containing car and motorcycle, and public transport, containing bus and taxi. The decision then happens in two stages. First, the individual chooses a nest, and then they choose an option within that nest. Each stage is modeled by a standard Logit model, and this structure lets the model account for correlations within a nest. The payoff is that the model now allows the choice between car and motorcycle to be more closely related than the choice between car and bus. Adding a train to the public transport nest will primarily affect choices within that nest. The relative odds among bus, taxi, and train will shift, but the private versus public split stays much more stable. For simplicity, take the first alternative as its own nest. The probability of choosing it is the exponential of VI1 divided by that same term plus a sum of exponentiated utilities of the other alternatives, adjusted by a parameter rho. That parameter rho measures the degree of correlation among the remaining alternatives, j equals 2 through c. Notice it appears twice, dividing each utility inside the sum and raising the whole sum to a power. If the first alternative is not chosen, the individual then chooses among the rest. The conditional probability of choosing alternative j, given that the first alternative was not chosen, is a standard Logit over the remaining alternatives, with each utility scaled by rho. Rho is what controls everything. When rho equals 1, the nested Logit model simplifies right back to the standard multinomial Logit model, and independence of irrelevant alternatives holds again. As rho decreases, the correlation among choices within the nest increases, which allows for more flexible and more realistic substitution patterns. The last variant we'll cover for nominal responses is the mixed Logit model. It's a multinomial Logit model that relies on both kinds of coefficients we've seen, a shared beta and category-specific betas. It takes this form. The first term is the multinomial Logit piece, and the second term is the generalized Logit piece. Both live in the same model. Breaking the two terms apart, the first vector, xi1j, represents predictors that depend on the alternatives. These vary across the different choices, but they share the same coefficient vector, beta. Think of travel time and cost, which genuinely differ from car to bus to bike. The second vector, xi2, represents predictors that do not vary across alternatives. These are constant across the different choices, but they get a different coefficient, beta j, for each category. Think of the individual's income or age, which is the same regardless of which mode they consider, but which may push them toward one mode over another. So the mixed Logit model lets you use both types of predictors at once, which is often exactly what real choice data looks like. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.